Welcome to today's lecture series. I'm going to basically take us through a simple problem. This is a prediction problem. We want to train our machine learning regressional model to take decision, and the decision that it's supposed to take is in regards to how it can actually be able to predict a given person's height if we know his weight. So in this case, we have a data set that we are going to load into our Jupyter framework. And our Jupyter framework, we're going to use Python programming language to craft some set of codes that can help us to be able to train a basic linear regressional model to help us achieve that set of tasks. So to begin with, I'll search for Jupyter Notebook Anaconda from my computer. And once that is done, I'll open a new shell. And on opening a new shell, we can actually be able to execute all our piece of code here to make sure that it helps us be able to achieve our predefined task. So most importantly, Python works with libraries. Libraries help us to achieve the basic operations that we need. So I can name this shell to be maybe linear regressional model. So I could say basic linear regression. Let me just call it linear regressional model. It may not be basic to everyone. So if I want to comment, I will use the hash button. So I can decide to take this to be libraries. After taking that to be in libraries, I will need to as well maybe put a function to define the function. I can plan. This is like the planning phase on what do I need to do in my work. I can also put something to load the data, and then I can put something for cleaning data. And in this cleaning of data, there are so many stages. We can look at the first one being converting units, because the kind of data that we have, we shall discover that the weight is in pounds. The weight is in pounds. So we shall have to convert. And if we have to convert that, you'll see 1 lbs is equivalent to 0.45359,237 kilograms. And then also the height is in inches, and it's very important to understand that 1 inch is equivalent to 2.54 centimeters. And then after doing that bit of cleaning, that's also part of the cleaning process, I can also be able to convert the columns that we are going to use to lists, because that's very important for us to actually be able to look at. And then finally, we shall build the model, because all the data will be clean. So we shall build the linear regressional model. And also in building linear regressional model, there are 3 stages. The first one will be basically the process of calculating the slope and the intercept. And then the second stage is in getting the regressional line, getting the linear regressional line, and I can calculate this from the slope and the y-intercept. And then the third one that we have is making prediction. And we can choose that we can make prediction when height is, or maybe when height is, I can take it to be 185, maybe 195.6. What is weight? Not weight just, but I can call this the predicted weight. So if we successfully do this, we need to take in mind that at any one point, we need to visualize our output. So this is my structure that I'm going to do. So to just support my work one, I need to call a Python so that I can be able to import this data. So I want to import pandas as PD. And after importing pandas as PD, I want to declare my data frame in the point of loading data to be pd.readCSV, read_CSV. And I want to pick the extension. My work is in the desktop, and in the desktop is in a folder called new folder, and this is my file. So I want to copy this path. After copying this path, I want to put it here. Kindly change this to forward slashes. And when you change this to forward slashes, you can actually be able to check this as well and see how it works. So I would preview my data frame and see how it works. And I can see this is my data, and the data has 10,000 rows. And out of the 10,000 rows, it has 3 columns. My rows are basically gender, height, and weight. And yeah, it has the respective gender of male and female. And if I look at this, plotting 10,000 entries in my axis will actually make my work very congested. So to simplify this, it's very much better that I look at ways on how I can be able to use some small manageable data to help me be able to do the desired prediction. So in this particular case, I want to put it under cleaning of data. I want to just pick one. Maybe let me pick the male data frame. And this male data frame that I'm picking, I want to only pick a particular element called gender in that data frame. Remember, it's case sensitive. And I want to assign that element gender. I want to assign that element gender to only help me pick the male component. And in the male component, I want it to only pick the first 200 features. Not 2000, but 200. So if that's the case, then I should actually be able to view this data set and see what do I have exactly in this particular line. And when I look at it, I only have 200 rows, 3 columns having male, weights, and the respective height. So this is very good for us to go. So still, these weights and heights are in pounds and inches respectively. So I want to do the conversion. So what I'll do, I will convert the male data frame that I have, which has particularly the height component, and I would want to take this to be male data frame, and in this particular case, still having that height component. And what I'm going to do here is I'll want to apply an expression on it. So we shall dot apply. And what am I applying in this function? I'm applying the parameters lambda. And I want to take lambda x being a function of a particular entity. So what I'll do, I'll multiply x by the conversion factor for height, which is 2.54. And to avoid doing another double typing, it's better I copy this. Then I just paste it, and I only replace this height with weight. And copy this and replace it here. Up. This is my weight. And then I'll want to also be able to pick this conversion factor to replace it with this 2.54. So meaning that is the value of the weight component. And if I want, I can be able to view my male data frame and see what it has. If you remember very well, you can see the figures have a little change. So this is now in centimeters, this is now in the respective kilograms. So meaning we're good to go. So if that is very clear, then we need to rethink about the next parameters. I can remove this since I'm not visualizing it at that point. I can also remove this because I don't want to visualize it at that point. So what I'll do now next, I want to convert my respective columns. The columns are heights and weight to lists. I can convert the respective height list. And what I'll convert it to, I'll convert it to the value in that male data frame that I have, and it was basically for height. Then I'll use the function to list. And I'll do the same thing also for my weight component, then I'll just change this to weight, and then I'll pick the specific column, which is weight. Remember, it's case sensitive, and if I did this, I can actually be able to view the weight component. I can also be able to view the height list, and I see how it is organized. So you can see this is now purely now on the respective weight and height, and it is being converted as a list. It's no longer in the other columnar kind of way. And this may not be very good for us. We need to be able to see this also properly put in a columnar kind of structure. So for us to do that, I would want us to introduce another package. Can I have this in a numeric array, something in columns, something that we can easily look at? So to simplify that, I'll import another package called numpy as np. And after importing that package, I want to define a given function. So that function, I want to define a function. Let me just call it maybe best fit line. And this function best fit line will feed on some two values. I want to call them x's and y's. And the function always have a column at the end of the day. So what features do we need? We shall need the slope, and then we shall need the y-intercept. Remember, in the line y is equals to mx plus c, the value of c is the same as the y-intercept. And m in that case the same as the slope. So the x and y's will be the xs and ys respectively. So if that is clear, then we shall return the slope and return the y-intercept. So what is the slope? The slope is got from an expression, and the expression that gives us the slope is the expression that looks at the relationship between the gradients, and that's why we had the change in y over change in x. So how do we have the change in y over change in x? We can actually relate this in the form of means. But now we're introducing mean, and we have not used the mean. So we can call also the mean function from statistics. From statistics, let's import mean. And once we import mean, then we can actually be able to bring it here and say, okay, my slope in this case will be, let me take it as mean, and the mean in this case is for x's. And let me multiply this by the mean of y values. And if that is okay, then I can subtract the respective mean for the product of the two, that is x's times ys. And when that is done, then I can divide the final result. Remember, you have to be very keen with your brackets. So what I'll do, I'll divide it with the value of the mean, and this mean is for x's, times the mean, and this mean is for y's, and not y's, but it should also be x's, sorry for that. And then I'll subtract the final mean for the product of the x's. You need to look at this formula and make sure it sorts accurate, you get a proper thing. So that's clear now. So if you look at the brackets, very important, you have to follow them. And then if I look at my y-intercept, I'm making c the subject from y is equals to mx plus c. So it's like I'll have y minus the value of the slope times x. So remember, this x now is the same as the x's and the y's values. So if that's the case, so let me define that as well. So I can say my y-intercept that I'm looking at is equals to the value of the mean, because wherever you have x, you shall take it as the mean value, and so not x but y. So y is equals to mx plus c, so that's y minus mx. So we shall just take y to be the mean minus m, which is the slope, and the slope is multiplied with the x's. So we can't just take it as the x's, we shall take the mean of the x values. So if that is okay, then we can run this and we see if it gives us an error, then we can really conclude that it has an error. The fact that this shell has compiled to 5, let's compile the second time, and we observe the fact that it has compiled to the next value, which is 6, means there is no error in this function. So if that function is defined, so what is x and what is y? And that's why I want us to look at next. So I want to introduce something here. I want to convert the columns as well, the two columns that we have, to column lists. And to do this specifically, I'm going to look at the x values and the y values. So for the y values, I'm going to take a numerical Python array. That's why we called it for the other function, I mean the NumPy library. So np, which means NumPy dot array in this particular case. For the y values, we're going to take it as the value of weight. So that will be the weight list that we already discovered. And in this weight list, we're going to declare it as a data type, which is a numerical floating function of 64 bits. And we can do the same thing as well for our y's, I mean for the x values. So I can say, what is it for the x values? So now instead of looking at the weight, so I can take it as the height list, and this will also be a data frame of that. So if that is cleared, we can still run this so that we're sure that whether there's an error or not. And we can see it has come to the next slide, so there is no error. So meaning the program is properly understanding that. So maybe just for clarity, we can be able to do some bit of visualization here. And our visualization should actually guide us on what the next values are like. And in this particular case, I want to take on the next values to be, first of all, I want a very beautiful graph. So I will take the style comment dot, let me use it as Seaborn. But if you look at it, we declare style. So we need to declare what is that style. And that's also a library that we need to look at. And still, we cannot plot anything without the matplotlib. So I will have to put the matplotlib dot pyplot as plt. And if that's the case, still from statistics we have taken care of. Let's also look at from matplotlib. Let's import that style function. And maybe just to complete this, I think it's also, since we're going to build our linear, anyway, we can get back to that. So this function can help us run that. So let's check. So we need to plot something. So I can do a scatter plot, plt.scatter for my x's and y's. And what is going to happen in this particular case is I'm going to take my labels, in that case to be the data points. And if the labels are going to be the data points, I will also want, on this particular case, to make it like when they meet each other, let them be a little faint so that we can see that point of intersection. So from a scale of 0 to 1, I want to take it to a 0.6 in terms of the faintness. And if that's the case, I want to take my color. Let me set the color to be the default green color. And if that is the case, I want the size of the dots also to be known. Let me take it as 75. So if that's the case, then I can do plt.show so that I'm first sure that what I have is properly visualized. So that's my visualization. So you can see how faint the dots are, and when they mix, we can easily see that they have met. If we're not declared that, then there would be a problem. So something comes up, we don't have a title, so I can do plt.title, and I want to call it linear regression model. And I want to label the x-axis, plt.xLabel. My x label in this case is going to be the height, and that height, remember, is in centimeters. And then I'll also want to do my y label, and my y label in this case is going to be the weight, and the weight is going to be in kilograms. Very good. So if that's the case, that means we are good to go. We can put a legend as well. Maybe we can put that later. Let's compile this and we see what features. So it's calling that, oh, what is this? It's not understanding this syntax. And why it does that is because it doesn't have quotations. So you can choose to put the double quotations or single quotations. That's real on your side. Good. So that is that. Maybe linear regression model is not enough. What is it? It's too small. Maybe I can say to predict the height given weight, because that's the problem that we have disclosed. So that's my greatest work. So I've plotted, and I think that's good enough to go. So if that's the case, I can also put a legend, plt.legend, as just a normal function. up and says it's not understanding that word legend. What is legend? And what is legend? It's not understanding what the legend function is exactly. But anyway, whether it doesn't understand it or not, it still goes ahead and plots it. But there's a problem. It's just this A. It's supposed to be legend. LE. So if I save this, and there we're good to go. It's just that it's very close, and that's why sometimes it can't show us. So maybe we can put this later. Let's recompile so that we have something standard. So if that's the case, meaning our data is good to go. So what do we do next? We can actually target now our final, we can target our final entries. Let's check, let's see how we can be able to insert these respective models. Like I want to see how I can be able to capture the slope. I've already defined the function up. So my function was returning the slope and the y-intercept. And what function, what values are these? So it's the slope and y-intercept for specifically the best fit line, because that's the function name that we have, and that should factor in the x's and the y values. So if that's the case, then I can also come in now and get my regression line. So I can say my regression line in this particular case is going to be equal to, let it get for me the slope times the x value, and if it does that, it should add for me the y-intercept. But remember, this compiler does not understand what it is. We're the ones who, maybe I should leave these brackets here, we're the ones who declared x and to be x's. So we can say for every x in x's. So like I'm telling my compiler that wherever you see x, let it be declared as x's. And that's good enough to go. And but I'm seeing something regressional line. We have not called a function, we have not called a library that can help us be able to do that regression line. So I can say from sklearn, kindly import linear model. And if that is okay, then I can plot this. And there we're good to go. It's trying to plot something, but we have not put anything for the curve to view. That's why you see it's still showing the other same old-fashioned curve. So I need to add something. What do I need it to view? So one thing that I needed to view is I want it to be able to plot for me a scatter. I want it to plot for me the linear regression line that we have already declared from there. And my linear regression line is going to be based on the x value, and it will be a regression line that I wanted to identify, and the label will be best fit line. Don't worry about the case sensitiveness, because this is just a string character. It's not similar to the function that we defined from up. And the color that I want it to have, let it have a little orange so that it gives a bit of a color contrast. And I can also declare its line width, maybe to be 4. You can try and can still compile without it. So let me check. If I plotted that, I'm good to go. Now that's my linear regression line. So meaning that linear regression line has been calculated. They look at the distance from the dots, the average of the distance from the dots to the actual line for all the dots. And the average of it when plotted is the one that has given this line. So meaning this line divides our data in a proper way that we can actually be able to understand. So since that is the case, meaning we can use that line. If we knew any point along this line, then we can actually be able to predict the respective weight. If we knew any point along that line to be maybe the x value, then we can actually be able to predict this point. But I see we altered these values, and that was basically our mistake when labeling the axis. We altered these values, so this should have been x and y. So we altered that. Let me just alter it afresh, and that's now good enough for us. So if that is okay, then I can now do my prediction. What would happen if I know my average man, if I knew my average man height to be equals to 195.6. So meaning my average man weight should as well be determined. Now, this comes from our expression. If I know x in the equation y is equals to mx plus c, and I've known my intercept, I know my slope. So meaning when I know x, I can find y. If I know y, I can find my x. And remember, our weight that we are getting is on the x-axis. Is it x-axis? If you look at our weight is on the x-axis, and our height is on the y-axis. So in this case, we know our height, which is y, and we want to find the value of x, which is weight. So if we have to make x clear from that expression, we can now say, okay, my average man's weight that I'm looking for is the same as the slope that I have times the average man's height that I will be knowing. And if this is clear, that means plus the y-intercept. So let me check. If I run this, I want to see how it can actually be able to get for me up. Still, I've not identified my point, my data point. So I need to identify that data point so that its color will be a little different from green, because now we cannot easily be able to tell where it is from here. So the best thing is, let's identify its respective color. So I want also to plot that same particular scatter plot, and I want to define a few values about that scatter plot. So one thing I know the average man height, I know the average man weight, and with those two values like x and y, I can define my label for that point to be my label for that point. I can define it to be the average, man weight, because I know the height, so I want to get the average man's weight, maybe even average prediction, just to stop confusing ourselves so much. And if I can predict that average prediction, let its color in that plot be red so that it can be distinct away from the green color and the orange color, and let the size of the dot be bigger to 100%, that's size 1. And if that's the case, let me save this and compile this. Whoop! I can see my point is at the extreme, and maybe that's a little complicated because there are a few data points here. Why don't I pull it around here? Let me bring it at 175, for example, maybe 175.6. So I could say what would happen when it is 175.6. And then I run this. I can see my point has really come at 175.6. So meaning when I know my weight of 175.6 kilograms, I can now easily be able to draw a line and predict that, okay, for that person of 175.6 kilograms, his average height is around 85 centimeters. So meaning our linear regressional model has been perfectly built to help us make a decision on the kind of predictions that we can have. And this is how best we can actually be able to use this linear regressional model to make particular predictions. And this applies for a huge line of events. It can apply for real world applications. We can deploy this so that when anyone enters any height of any person, then we can say, okay, we expect this man to be this weight. If anyone enters anything, then we can say, okay, we expect this man to be this. And much more applications can find use of this. So this final output can be exported. You can copy this image, you can save image as, and later reuse this kind of application. So I think for today's lecture series, we can be able to end here. We look forward to having a fruitful discussion with you in our platforms. Have a good day. Right.